Hello everyone, this is Professor Kang-Han Oh, and today I'm going to talk about the laser modeling simulation tools. So uh, from previous lectures, you have learned the basics of the lasers. So for instance, if you have a mirror 1 and then if you have a mirror 2, this will form a optical cavity. And then for a specific set of mirrors, and for which composes a cavity, a certain cavity, then it has a cavity modes depending upon the boundary conditions of those mirrors. And then if we put an optical gain medium inside the cavity, then we pump it either by end pump or side pump. Then there is a stimulated emission process going on, and then as a result, we get the lasers coming out. So in this case, what we need to analyze is that we need to think about the cavity mode, pump mode overlap, and then from this you get the rate equations, which defines the net gain. And then we have a laser power and the output mode, and then that are the result of what we have learned in the previous classes. Okay, then if we want some certain laser simulators, and there are several questions we should ask. What can be done in our laser simulators? And what are the input parameters that can be changed? And then what are the outputs of these simulations? Can I get the laser power versus pump powers, or can I get the mode profile of the actual lasers, or other thermal effect, etc.? And those are the things we should ask. And another thing is that is the simulator tool is realistic. That means if we have a real lasers, does the simulation result coincide with the actual measurements? And then that are the very important questions. So here is the widely used laser simulators, which is called LASCAD. And then if you click this, okay, here is the home page of the LASCAD, and then it is a kind of abbreviation of laser cavity analysis and design. So that is the LASCAD, and then it is very quite a stable and a very reliable company based on the Munich, Germany, and it has several features. Today, what I'm going to do is we are looking at this LaserCAD. The good thing about LaserCAD is it is free downloadable, and that it has a very detailed manuals and tutorials. So you can just read the manuals and actually try those simulations step by step. And the user interfaces is pretty good, even though it is not that friendly, but it is pretty good, so that you can actually simulate the lasers using their pre-downloadable programs. Of course, you should buy more sophisticated versions, but at least you can try the free software version as well. Okay, so we will talk about LASCAD. So here is the PowerPoint file from the LASCAD company, and it is an introduction, and then it is written by Dr. Konrad Altmann, and then I will follow this. Some of the slide has been summarized and then I will follow those presentations. Okay, so if we think about what can be the numerical analysis, so numerical analysis of the 3D nonlinear interaction of the optical fields in a cavity with the thermal effect. Okay, so thermal effect such as the temperature-dependent refractive index distribution, observed power distribution, doping distribution, population inversion, etc. is of growing importance to optimize solid-state lasers. So these are the demands for simulations, and these are some of the key issues in the solid-state lasers. And in order to do that, to model these complex interactions in a laser cavity, LASCAD software combines the necessary simulation tool onto one package. And based on quantitative understanding of the multiphysics effect in a laser cavity, LASCAD allowed the laser engineer to optimize important features of a laser, like beam quality and laser power output. So here is the very important important features of a laser simulations. What's the beam quality is? So we call it M square. So M square means is that how circular it is, how uniform it is, and then how behave like a Gaussian beam. If it is really Gaussian beam, then M square should be 1. And then everybody wants M square should be near the 1. Okay. And the laser power, laser output power, is also another very important characteristic of a laser, and how much power we can get. Is it CW, continuous wave, or pulsed? And then what is the average power, etc. So beam quality and the laser output power is very important characteristics of lasers, and then by optimizing parameters of the laser cavity and gain medium, and you can actually estimate those two key parameters, beam quality and the laser output power. So LASCAD offers a thermal and structural finite element analysis. So it is based upon finite element analysis to solve the differential equations. And then for the case of beam propagations, they are using ABCD Gaussian beam propagation method. And you have already, you might have already learned about this ABCD, which means any optical element is represented by the 2x2 matrix ABCD, and then you have a certain height and angle, height and angle. This is the input, output. And then ABCD could be anything. It could be mirrors, it could be reflectors, lens, whatever it is. We can represent the 2x2 matrix ABCD. And the physical optics beam propagation (BPM) is also a very useful simulation tool. And then computation of a laser power output and the beam quality is made within the software, which is very useful. And then in the case of pulsed mode, especially Q-switched mode, and we call it DMA, dynamical analysis of multimode. And if we can excite not the single mode, but we are talking about the mode here is the cavity mode. And then we can have some kind of a temporal response in a cavity such that we can make a pulse by the interaction among those modes, okay, so that we can have various tools. So it has an optical workbench and the laser engineering tool and the educational tool, so that it can be used both. So as an educational tool, actually I'm using it here. In fact, this is probably the only free downloadable laser simulation tool, so that it is quite worthwhile to investigate its functions. So optical elements like mirrors, lenses, and the crystals can be added, combined, and positioned, adjusted, or removed with a mouse click. And astigmatism of resonators and crystal is automatically analyzed. And FEA, ABCD, propagation, and the dynamic multimode analysis, and the physical optics BPM can be easily be started from a menu bar. Okay, so that you can, if you just look at it, then there is some kind of options. You can do the either finite element analysis or ABCD, DMA, or physical optics BPM. Okay. So as a first example, FEM or a finite element analysis, FEA is used to compute temperature distribution, deformation, and the stress or fracture mechanics in a laser crystal, or to analyze the effect of a different cooling system. So that FEA is usually related with the thermal issues. Thermal issues in the laser is very critical. In fact, even though we did not in textbook, normal textbook, we did not include the thermal effect in detail. But in practice, if you want to use the lasers for industrial use or military use, or even scientific use, you need to have a very stable lasing. And then this is only guaranteed by the temperature control, so that you have a huge set of a water cooler, for instance, to stabilize the temperature of crystals. So crystal is constantly bombarded by the pump lasers, and the pump laser is in fact absorbed by the gain medium. And then due to the energy difference between the pump photon and the laser photon, the difference is just turning into the heat. So basically you generate the heat by the lasers all the time, and then as heat accumulates, the temperature goes up. And then this will change the whole story. For instance, the gain and absorption. And then the laser output is going to be a function of time, so that it is not desirable, so that what they have done is to try to stabilize the thermal effect by cooling. And in order to understand the cooling, you need to understand, first of all, what is happening inside the laser crystals or optical gain medium if they absorb the pump photon. And that can be done by the finite element analysis in the LASCAD. Okay. So that you can do it. And pre-designed FEA models with adjustable parameters such as the dimensions of crystals or material properties are provided to assist the engineers with the different configurations, so that they have many types of lasers already. So you can just bring them in to the computational window by simply clicking it. And 2D and 3D graphic tools are available to visualize the pump light distribution and boundary conditions and the result of FEA. Okay. And the pumping, you can have end pumping or side pumping. Okay. So that end pumping is possible, and end pumping. And side pumping is also possible. Okay. So here is the main menu. If you download and then install it and then open it up, and then you can have this menu, and then you can have crystals and pumping configurations are shown, single or dual end pumped, cylindrical load, and etc. 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 Basically, it is end pumping or side pumping, or it could be a rod or slab. Okay. So, and then here you can choose the pump light condition, boundary conditions, and material parameters, bumping materials, and then FEA options. This is possible. You can have a mesh, very small meshes, or optimal mesh, or larger meshes. You can have it. Composite crystal can be used with all models, for instance, rods with undoped end caps. Sandwiched slabs with the doped and undoped layers can be modeled, and the heat sinks can be also included, which is very practical. So here is the typical example of the cavity here, meter 1, meter 2, and then here is our optical gain medium. And you can see that the green lines are actually the cavity modes, okay? And then here is some kind of a gradient, the bright yellow and the dark yellow, and the dark yellow is where the temperature is going up, okay? So when you do the FEA analysis for the temperature, you can find out actually temperature profile like this: hot, less hot, and cool, for instance, like this. For the case of when it is pumped here, okay, and pump. And the temperature distribution in a rod with the undoped end caps. So if you look at it, this portion does not have any dopant or optical gain, such that there's nothing to be absorbed, so that just pump photon passes through without any absorption, so that you can have this kind of a thermal confinement in a certain region along this composite optical gain medium. And furthermore, you can utilize the side pumping. So crystal is actually looks like this, and then it is pumped by the side. Okay, and this can be also simulated. So FEA results will give you temperature distribution, mechanical deformation, or stress within the optical gain medium rod, and then this will give you. This will be combined with the ABCD Gaussian propagation code or physical optics propagation code, which is we called BPM. Okay, and then this will this combination will give you the laser simulations. Okay. So the modes obtained by the Gaussian ABCD matrix approach can be used to compute the laser power output for the CW operations as well as the Q-switch operation. In the first case, the steady-state radications are solved by the use of iteration procedures. Okay, here is the case. So it shows a very good agreement. Here's the these are measurement, and these are the computations, and it shows very good agreement. Okay, so neodymium doped YBO vanadium oxide, yttrium vanadium oxide crystals with a 0.27 atomic percent of a neodymium. Okay, and then it is widely used laser crystals, and then it shows a very good agreement between the measurements and computations. In addition to solve the steady-state radiation, LASCAD offers a new tool for the dynamic analysis of multimode computation and the Q-switching operations, and as a result, you can get a pulse simulations. So the horizontal axis is time, and then this axis is the power. So actually, these are the pulse from a cavity. Okay, so you can actually calculate the pulse shape out of this simulator, which is very useful. For cases where parabolic approximations and ABCD Gaussian propagation codes are not sufficient, FEA result alternatively can be used as an input for physical optics code using a FFT split-step beam propagation method. Okay. And the physical optics code provide the full 3D simulations of the interaction of a propagating wavefront with the hot thermally deformed crystals without using parabolic approximations. So these are the simulation iterations, and then it shows that by number of about 100 iterations, it converges to certain value, and then we estimate these are the actually beam radius, and then as you can see here, the iteration of the calculation is not that much, so we order of 100. Okay, so which is very good. And then we need to know that the wave optics code takes into account diffraction effects due to aperture misalignment effects observed from power distribution and gain saturations. And this is very important. It is the detail of the laser performance. And these considerations will give us some very realistic result. Okay. And these are the intensity distribution at the output mirror, which is the actually laser beam profile. Okay. And then you can also calculate the phase distribution as well. You can see that the phase is distributed like this. Okay. In addition, the wave optics code is capable of numerically computing the spectrum of resonator eigenvalues and also the shape of the transverse eigenmode. An example for a higher order Hermite Gaussian mode is shown here. Okay, so you have heard about the TEM22, for instance, and this LASCAD can calculate the higher order modes. And then in some cases, you need to calculate those modes either in the C-table operations or Q-switched operations. And very interestingly, this LASCAD can provide you to calculate the individual cavity modes. Okay. So here are the manual. So you can actually look at the manuals one by one. So here's the windows of the LASCAD when you open it, when you start the program, and then there are several tabs to be analyzed, and then there's a DMA and BPM and several things. I'm not so sure whether this is pre-downloadable can be used for DMA and BPM, but I'm sure that it will give you some of the mode calculations and some of the basic calculation. If you run the free downloadable program, there are finite a set of pre-embedded conditions of the resonators and the optical gain mediums, and then you can play with it. Okay. And then in addition to manual how to use the software, there are tutorials. I'd like to suggest you to try two different tutorials. One is the end pumped, and the tutorial 2, this is the side pumped. Oh, something is wrong. But anyway, if you go there, and then you can find out those informations. Okay. And as a homework, create your own laser and find its performances using LASCAD. And the LASCAD can be downloaded in this website here. But if you click it, you need to fill in your informations, such as your name and affiliations and your emails, and then you can download your this trial version. Okay. Okay, this is the end of my lecture today, and it is about the lasers. Okay. So here is the things. So we need to start with the mirrors, and then this forms a cavity, and then this cavity defines the cavity modes, and then if we place the optical gain medium, there is an interaction can take place by pumping it. Okay, either end pump or side pump, and then as a result of these interactions, and you can get the lasers at a certain mode. Okay, certain cavity mode, and that can be simulated with the LaserCAD. Thank you.